this video, we would be learning about the history of complex analysis. Before we go ahead and start learning the mathematics of complex analysis, it is important for us to know how complex analysis evolved, what is the history of complex analysis, who are the people who discovered complex analysis, and how the imaginary numbers and other related important concepts developed. So this video would be dedicated towards learning the history of complex analysis, and I would be keeping the mathematics part apart because this will be a fascinating journey where you will learn how the history of complex analysis and other related concepts developed. My name is Shaunak and you are watching this video on my channel Physics for Students. A warm welcome to learn about the history of complex analysis. So first let us look into what are the topics that we are covering today. So first we are covering what is a complex analysis, a basic layman's understanding. Then we will understand the discovery of complex numbers, how the cubic equations emerged in history, what are the difference and how the quadratic and cubic equations helps into our better understanding, how imaginary numbers were developed, and the developments by Euler, Argand, Gauss, and the important contributions of Richard Hamilton, Cauchy, and Riemann. This would be a video which is considered to be the foundation stone or the foundation before studying the complex analysis, because until and unless we understand the history, the entire mathematics becomes too boring. So first we start in understanding in a very easy language what is a complex analysis. Now you see, complex analysis is traditionally known as the theory of functions of complex variable, is the branch of mathematical analysis that investigate functions of complex numbers. So complex analysis is a theory of functions of complex variable, and it is helpful in many branches of mathematics including algebraic geometry, number theory, analytic combinatorics, and applied mathematics. Complex analysis is one of the classical branches in mathematics with roots in the 18th century and just prior. So important are the algebraic geometry, which is also important, number theory, which deals a lot with complex analysis, combinatorics, yes it does, and applied mathematics, including quantum mechanics. As you have seen in my previous videos, I've started a new series of videos which is called the mathematics of quantum mechanics, and in the beginning of those videos I have dealt in details about complex numbers, complex plane, etc. So yes, quantum mechanics deals a lot with complex analysis, and as well as thermodynamics is involved in complex analysis. So it includes important figures like Euler, Gauss, Riemann, Cauchy, and Weirstrass, and many other more in the 20th century. So, and also Cauchy. So complex analysis in particular, the theory is including conformal mappings, has many physical applications, and is used throughout analytic number theory. Now in simple terms, the complex analysis we can also tell that it is an extension of the calculus of real numbers to the complex domain. So the calculus which we learn is basically dealing with real numbers, and if we extend it to the complex domain, then it happens. So here you see that in modern times it has become very popular through a new boost from complex dynamics, from the pictures of fractals produced by iterating holomorphic functions. Another important application of complex analysis is on string theory, and which examples conformal invariance also into quantum field theory. So this is all in all what we can tell is all about complex analysis. So you can summarize thinking that it is basically an extension of the real number into complex plane, as well as extending the theory of calculus from the real domain to the complex domain. Okay. So it is extensively used, as you know, it is used in engineering, electrical engineering, nuclear transmission, theoretical physics, especially in quantum physics and quantum mechanics, and it also deals a lot with data science, because data science deals with a lot of data, a huge amount of volume of data which needs to be formatted so that we can get the understanding of a particular business unit or anything more. So these are some of the important, I would say, applications of complex analysis, starting from the engineering field and ranging up to data science. Okay, So as we understand and go deep into complex analysis, the first thing that we need to understand is that how the complex numbers are developed. And in this part of the video and the coming, I would be discussing about the discovery of complex numbers. Now let us consider a quadratic equation, something of this form: x squared is equals to mx plus n. Now from elementary school we have learned that how to find its solution, that is all the values of x that satisfies the equations in the form this one: x equals to minus b plus minus square root of b square minus 4ac by 2a, and in the general equation this ax squared plus bx plus c. So by rewriting this above equation as x square, if you can write this one and this one, what we get this one mx equal to this one, and then we get m upon 2 plus minus this. So if we plot this equation into this, then we can observe geometrically that it represents the intersection of the curve this one y equal to x squared parabola with the line y equal to mx plus n. And here you see this is the equation, or rather I would say the graph of parabola. And when we are plotting this, you can see that these two red dots, that means they are intersecting at two points. So again, to tell you that if we plot these two graphs, the equation 1, and we can observe geometrically that it represents the intersection of the parabola with the line y equal to mx plus n, and we can see that it intersects with these 2 points. Okay, so we go ahead with this part. And what we come to know from here is that there are 2 points of intersection. That means there will be 2 solutions. There is only 1 point of intersection point, then there will be 1 solution. And if there are no intersection points, there are no solutions. Now, this is nothing great. I mean to say, this was used to known by the Babylonians dated around 2000 BCE, that the Babylonian civilization possessed the quadratic formula which can be found in the inscriptions, etc. What is particularly important is that if we find, go back to this equation x squared equal to mx plus n, and if we take the values as n equals to 0 and n equals to minus 1, then putting this value, what we get is this one: x equal to plus minus square root of 1. Now, this is something which is new to the mathematicians during that time. So it was a problem, it was a point of confusion. And that is why we call that how we can interpret this value. So from here, where we are going. Now, we know from the elementary school calculus that we cannot take the square root of a negative number, right? Then how do we interpret this value? What is going wrong? Okay, so you see x equal to plus minus square root of minus 1. Now, if we can take it to the equation of parabola where y equals to x squared and the line y equals to minus 1, as you see, do not intersect with each other. Here is the figure which shows that we can plot, that means in a value where y equals to minus 1 is not intersecting, and it is just lying on the minus 1, that is in the negative y quadrant. Okay, so this actually, it is argued that this very problem, that how can we interpret this new unknown number, it led to the invention of a new number which is denoted by I, and which is equal to square root of I minus 1, and which is then termed as imaginary number. Okay, so square root of minus 1, if it is a common practice to point out in a course of mathematics that the complex number is denoted by a plus b square root of minus 1, are basically required to solve certain quadratic equations. For example, this one, x squared plus 1 equals to 0. However, complex numbers emerged, in fact, from the need to solve the cubic equations. Furthermore, so how did complex numbers emerge, and what problems will they solve, or what problems did they solve? That is basically the importance. So where did the complex numbers come from? How did they emerge? And what problems did they solve? Because right at this moment, we understood that this unknown number, which is quite different from that of quadratic equation, because in quadratic equation, it is something that we find that the point do not intersect and y lies in the negative quadrant. Whereas with I as an imaginary number, we are really left with no clue and we really don't know to found. So how did complex numbers emerge and how it is found? So remember that as you can observe, no matter that the quadratic equation was not the problem. It forced the mathematicians to ponder over the mystery of complex numbers. It was the cubic, which is x cube equals to px plus q. Now here you can see this is a graph which I have plotted where y equals to x cube. It can be ax cube. That's a kind of a nice parabola, and here you can see that this line is intersecting at 2 points x0, x1 and x2 and x3. X0, x1 and x2. Now I cannot make further graphs over here because it would look too cumbersome, but you should remember one thing, that no matter what line is defined by the parameters p and q, you can change the values in p and q, it will always intersect the cubic somewhere. This is important. Even if the line p and q, here it is, even if the line px plus q is perpendicular to the x-axis and far from the origin, it will also intersect. Even if px plus q is far from the origin and p and q have huge values, still they will do. Why? What is the reason? Because cubic ranges from minus infinity to plus infinity. That means there is no line that you can draw that would not intersect the cubic. This example is very different from the quadratic case, because for a parabola x squared, you would define a line mx plus n that would intersect. So the question is why? So the first thing is that no matter what line you define, p and q will intersect cubic somewhere. Even if px plus q has got a perpendicular to the axis, and even if px plus q has huge values, it will always intersect because cubic ranges from minus infinity to plus infinity. So again, here is an important point, that remember, this is not the case with quadratic equations, because we saw that when we are plotting the quadratic equations, we can get a line y equals to minus 1 which lies in the negative quadrant. So parabola y equal to ax squared, we can define mx plus n in such a way that it would not intersect the parabola, and the left hand side illustration shows that. So this marks a big difference. This is the most important factor which led to our foundations of our complex numbers or imaginary numbers. Okay. So now the question is that we dealt a lot that cubic equations caused a lot of disturbance. Cubic equations actually resulted in the foundation of other investigation in mathematics. Now what we will learn is that what is and how did cubic equations emerged. Now 4.5 centuries have elapsed since complex numbers were first discovered. And as you know that it is probably you're aware that the term complex number refers to this one, a plus ib, where a and b are ordinary real numbers, and unlike any ordinary number, I has a property that is I square equals to minus 1. Now this discovery would ultimately have a profound influence on the whole world of mathematics, unifying much that had previously seemed disparate and explaining much that had previously seemed inexplicable. Now so this is something important. Now here comes the book. Girolamo Cardano's Ars Magna, which means the great art, which appeared in 1545, is conventionally considered to be the birth certificate of complex number. The Ars Magna, that means the great art of 1545, is an important Latin book on algebra written by Girolamo Cardano, and it was first published in 1545. It is considered to be one of the three greatest scientific treatises of the early Renaissance, together with Copernicus on the revolution of heavenly sphere and Berzelius on the fabric of human body in 7 books. The first edition of these books were published within a 2-year span of 1543 and 1545. Now, it is well known that the solution of this x cube equal to px plus q was developed by Italian mathematician, and Girolamo Cardano showed that this could have a solution which is given by this. Now, he took this formula from his predecessor, that is Niccolo Fontano Tartaglia, and what he found was that this book, which actually is the foundation of complex numbers, and he found the cubic solutions for this, first published algebraic solution to cubic and quartic equations, and Ars Magna contain first occurrence of complex number, which is explained in this chapter. Okay, so let us consider this equation x cube equal to minus 6x plus 20. Now, if we take the values, say for example, p equals to minus 6 and k equals to 20. And if we put the value in this cubic equation, then we get this. This was actually what Girolamo Cardano showed in his book Ars Magna. And by simplifying, we get x equals to 2. Putting the values of x equals to 2, we get this, which leads to this. So now this formula seems to work very well. At least, I mean to say, you can find out the overall solution to this. So this is an example. Now this actually led to what is called the discovery of imaginary numbers. And in this part of the video, we will be talking how imaginary numbers were discovered. Now here comes one of the greatest mathematician, Italian mathematician, Rafael Bombelli. Was an Italian mathematician. He was born in Bologna. He is the author of Treatise on Algebra and is a central figure in the understanding of imaginary numbers. He was the one who finally managed to address the problem of imaginary number. In his 1572 book La Algebra, Bombelli solved equation using the method of Tartaglia. He introduced the rhetoric that preceded the representative symbols plus I and minus I and described how they both work. So he is the one who finally managed to address the problem of imaginary numbers. Bombelli is generally regarded as the inventor of complex numbers, as no one before him had made rules for dealing with such numbers. And in his book entitled Algebra, Bombelli gave a comprehensive account of the algebra known at that time. And he was the first European to write down the way of performing computations with negative numbers. So I hope it is now clear that how Rafael Bombelli's contribution and formulation of the complex number actually evolved through this. Okay, so here is the book, La Algebra. This is by Rafael Bombelli, and because he knew some very simple way of explaining things. So here you see he has written plus by plus of minus makes plus of minus, minus by plus of minus makes minus of minus, plus by minus of minus makes minus of minus, minus by minus of minus makes plus of minus. So it goes along with that. So Bombelli actually had the foresight, he had the vision to see that imaginary numbers were very crucial and necessary to solve quartic and cubic equations. Now, if we consider this equation x cube equal to 15x plus 4, and we can find out that if x equals to 4, it has a solution. Why? You see this kind of a graph where I have drawn this, and you can see that if you plot x equals to minus 4, and you can see here it has got a solution, and it is cutting at 3 points, this, and this. Right? So from here, using x equals to 5x plus 14, and taking p is equal to 15, q is equal to 14, he got into this, which resulted into this. Now, here we encountered something very unusual. This is, during that time, had an unusual value. So if Cardano's formula was correct, this number must be equal to 4. Now, this must be a kind of a nonsense, and the value cannot be real. So because inside the cube root, we are taking the square root of a negative number, an absolute impossibility during that time. And Cardano also encountered this difficulty, but he did not, maybe due to some reason, he did not face it up. And he did once mention imaginary numbers, but in connection with a quadratic equation, and accompanied by the comment that these numbers were as subtle as they are useless. So it was Cardano who actually, faced this thing, but he was unable to solve it out or spell it out, and he just told that it is as subtle as they're useless, until it came to Rafael Bombelli, and Bombelli considered this to be a very wild thought. Okay, so Bombelli overcome this difficulty by seeing the weird expression, this one, as nothing but Cardano's formula, which gives, x is actually real. So here you see that Cardano's formula gives for x is actually real, but expressed in a very unfamiliar manner. This insight did not come, as Bombelli wrote in his book La Algebra. And although to many this will appear an extravagant thing, remember he's using the word extravagant to mention that, because even I held this opinion some time ago, since it appeared to be some sophistic that true, nevertheless I searched and found the demonstration, which will be noted below. but let the reader apply to his strength of mind, for otherwise even he will find himself deceived. So you understand, during that time, I'm talking even during the Pythagorean time, when people used to worship numbers, something which has got no value, something which is imaginary, by orthodox mathematicians during that time, or even by physicists, it is considered to be something very difficult to be perceived, as by Cardano, and he left it something like that, and it was later taken up by Bombelli. Okay, so what was Bombelli's insight? Now, Bombelli's great insight was simply to treat square root of -1 as a number and to operate it with specific arithmetical rules, the same kind of rules that we follow nowadays. And he found that if this cubic root of this and this equals to this, right, and substituting the values in this big equation, what he got is this, right? And then what he did is that he showed that the square root of negative numbers cancels out, as you can see here, and concluded that x equals to 4 is actually the solution of this x cube is equal to 15x plus 14, which is obtained from Cardano's formula. And the trick works only in few cases. However, it helped to understand the mathematician during that generation, and for to all of us, that imaginary numbers, and to take their cube roots to manipulate them when they appears aside real numbers. So this was actually the calculation which I will show you, the original paper of Bombelli. So what he found was this: putting the values, he found this, cancelling out the root, he concluded that x equals to 4 is the solution for this cubic equation. So this is actually the original paper, and as you can see, Bombelli did not have at his disposal the power of today's algebraic notation, and his computations were limited to numbers in real domain. In fact, most of the Italian mathematicians during that time tended to think of cubes or square as geometric objects rather than algebraic quantities. However, he is credited for proving the reality of the roots of the cubic x cube equal to 15x plus 4. Now, Cardano's formula forced mathematicians to confront square roots of negative numbers. The historical incident is another example that negates the widespread view that mathematics is made up by mathematicians. As is often the case, the mathematics itself that speaks to of us from this time on, imaginary number lost some of their mystical character, although their full acceptance as bona fide numbers came only on the 1800s. So now we will see that after the development of complex number and finding the cubic root of x equal to 4, what Bombelli did, what are the new and the later developments which took place in understanding our concept of complex analysis. Here is the famous person, Rene Descartes, and in his book Geometria, he's told that neither the true nor the false negative roots are always real, but sometimes only imaginary. So we are talking of the era between 1596 and 1650, when this great mathematician and philosopher Rene Descartes actually contributed a lot in finding out the complex number. Okay, so it was during that time that another German philosopher and mathematician, Leibniz, mentioned the imaginary number is a fine and wonderful resource of the human spirit, almost an amphibian, being and not being. So complex numbers are called impossible and imaginary, and the great mathematician Leonhard Euler even made a mistake by calculating square root of -2 multiplied by square root of -2, which led to -6. So all it was going on, and it was a problem that we are unable to define what is a complex number. Now the answer came from somebody whom we know as Jean-Robert Argand. Now he was an amateur mathematician. In 1806, while managing a bookstore in Paris, he published the idea of geometrical interpretation of complex number, known as, now we know as Argand diagram, and is known for the first rigorous proof of the fundamental theorem of algebra. Further, Caspar Wessel was a Danish-Norwegian mathematician and a cartographer. In 1799, Wessel was the first person to describe the geometrical interpretation of complex number as points in the complex plane and vectors. And lastly, no mention, no references required, the prince of mathematics, Carl Friedrich Gauss, made immense contribution in the field of our understanding of complex number and complex analysis. Okay, as you see, this is a kind of a simple, very elementary XY axis, and this is what is called Argand plane, which was later named as Argand-Gauss plane. And the complex plane is called Argand plane or Gauss plane. But remember that the publication of Argand and Wessel went unnoticed because of the dominant figure of the Prince of Mathematics, Karl Gauss. But the popularity of Gauss assured dissemination and acceptance of complex numbers as points in complex plane. And I have not mentioned here, but you can know that how this C, which is quite bold, how it measures, and that is how we denote complex plane today. Okay, so Leonhard Euler actually standardized the notation of I equals to square root of -1 and used imaginary numbers to solve quadratic and cubic equations, in spite of the fact that he was still suspicious of these numbers. And in his book, The Algebra, he mentions, since all numbers which it is possible to conceive are either greater or lesser than 0 or 0 itself, it is evident that we cannot rank the square root of a negative number amongst possible numbers, and we must therefore say that it is an impossible quantity. In this manner, we are led to the idea of numbers which from their nature are impossible and therefore are usually called imaginary quantities because they exist merely in the imagination. So here comes the first coining of the term imaginary number by the great Swiss mathematician Leonhard Euler. And here in his book, The Algebra, he mentions that because it is something which is beyond the comprehension and can only remain in imagination, so we call it as imaginary number. Now, the first rigorous definition of complex number was given by this Irish mathematician William Rowan Hamilton in 1833. He proposed to the Irish Academy that complex number a plus ib can be considered as a couple a comma b with a and b as real numbers. Then he defined it as this one, which is the addition rule, and this one as the multiplication rule. This is in fact an algebraic definition of complex number. From the didactic and heuristic point of view, it is preferable to have complex numbers introduced through our geometrical interpretation. But from the logical point of view, the theory of couples is much more satisfying since it shows the consistency of the theory of complex numbers starting from the consistency of the real numbers. Finally, there are few other mathematicians. One was Augustin Louis Cauchy, and Cauchy actually developed what is called the theory of complex integral calculus. Using imaginary number, Cauchy was able to evaluate real integrals which get fascinating values like this and this. Finally, the two other important mathematicians are Karl Weirstrass, and who appeared in the mathematical scene about the middle of the 19th century. Weirstrass developed the theory from a starting point of a convergent power series, and this approach led towards more formulation of algebraic developments. And the granddaddy of mathematics, Bernhard Riemann, who contributed a more geometric point of view on the study of complex functions. Riemann's ideas had a tremendous impact only on complex analysis, not only on complex analysis, but also upon mathematics as a whole, though his views took a lot of time and it took generations to understand that. So we come to the end of today's video, and I would just like to show you the timeline how these things actually started. And you see, it started with Tartaglia, and then it went to Girolamo Cardan, who first framed that, followed by Rune, Descartes and Leibniz and Leonhard Euler, Caspar Wessel, followed by Argand, and who we call it as Argand plane, followed by Gauss's impact on complex analysis. Hamilton was the first to give a formal definition, followed by the Cauchy and Karl Weirstrass and Bernhard Riemann, who get a much more of a geometric interpretation. So right on your screen, all those important mathematicians, all those important contributions actually led us to what we call it complex analysis today, and that would be the subsequent process of discussion and subsequent lessons in my next videos when I would be dealing with the mathematics of complex analysis. So how do we summarize? We summarize that we got a brief understanding on complex analysis, how complex numbers were discovered, quadratic and cubic equations. We learned more about cubic equation. We learned about Bombelli's discovery and further developments of complex number. The first definition by William Rowan Hamilton and further contribution by Gauss, Argand, Euler, Cauchy, Weirstrass and Bernhard Riemann. So that completes our today's video, where I try to give you a kind of a basic layman's approach towards complex analysis, how the discoveries were made. Please subscribe to my channel Physics for Students. Click on the bell icon and click on all to get all the notification from Physics for Students. And please do put up your comments so that I can know how this video has been and how things are going. What did you enjoy and what are the things that you have in your mind so that you can ask me questions. Thank you for watching this video. This is Shaunak signing off from Physics for Students today, promising you to be back very soon with another fascinating video on physics and mathematics. Till then, goodbye.
Thank you for watching this video. We appreciate your time and patience. If you want to connect with us and provide further feedback, comment or suggestions, please email us at contact.physicsforstudents@gmail.com. You can also follow us on Facebook, Instagram and LinkedIn. See you soon in the next video.